Data Analysis and Visualization, Unit 1, Shape of Data. Shape of Data. Univariate data refers to data that involves just one variable or characteristic. The term uni means one, so we are focusing on a single aspect of the data. For example, if we only look at the heights of students in a class without considering any other factor like their weight, age, or marks, that is univariate data. So a list like 150, 160, 155, 165, 170 in centimeters is univariate because it only tells us about one thing, the student's heights. This kind of data helps us to understand patterns or trends related to that one variable. Whereas multivariate data involves more than one variable. The word multi means many. So multivariate data includes two or more characteristics for each observation. It also allows us to study the relationships or patterns between these variables. For example, if we record students' ages, heights and weights, we are dealing with three variables at the same time. We can then compare or analyze how these variables might be related, like whether taller students tend to weigh more or how height changes with age. This type of data helps in making deeper and more meaningful conclusions. Frequency distributions. A frequency distribution is a way to organize data so we can easily see how often each value or range of values occurs. Instead of looking at a long list of numbers, we group similar values and count how many times they appear. For example, if we look at how many hours students study, we might group the hours into ranges like 1 to 2, 3 to 4 and 5 to 6. Then we count how many students fall into each group. If 5 students studied for 1 to 2 hours, 8 students for 3 to 4 hours and 3 studied for 5 to 6 hours, we can clearly see where most of the students fall. This helps us understand the overall pattern or trend in the data. These are the steps to create frequency distribution. We are given marks scored by 30 students in a math test. To better understand a large set of marks, we can group the data into classes or intervals. Instead of looking at each individual mark, we organize them into ranges like 5 to 6, 7 to 8 and 9 to 10. Then we count how many students fall into each range. For example, 7 students scored between 5 and 6, 12 students scored between 7 and 8 and 11 students scored between 9 and 10. This makes it easier to see which score range is more common and helps us understand the overall performance of the class. Second step, add a cumulative frequency column. Cumulative frequency shows the running total of observations up to each class. It helps us understand how data builds up across the ranges. In this example, 7 students scored between 5 to 6 and the total number of students scoring up to 8 mark is 19. By the last range 9 to 10, the cumulative frequency reaches 30, which means 30 students took up the test. This method gives us a better picture of how marks are distributed overall. Measures of central tendency. Measures of central tendency help us understand the average or middle of a dataset. The three main measures are mean, median, and mode. The mean is the average found by adding all the values and dividing by the total number of values. The median is the middle value when the numbers are in order, and the mode is the value that appears most often. For example, with the test scores 50, 60, 70, 80, 90, the mean is 70, the median is also 70, and there is no mode since no number repeats. These measures gives us a sense of where most data points are centered. Spread. The spread tells us how much the data varies or how spread out the values are. The range is the difference between the highest and lowest values. Variance tells us how far each number is from the mean on average but squared, and standard deviation is the square root of variance, showing how spread out the data is in the same units as the original values. For example, in the heights 150, 160, 155, 165, 170, the range is 20. These measures help us understand if the data points are closely packed or widely scattered. Range. The range tells us how spread out the data is by simply subtracting the smallest value from the largest. It gives us a quick idea of the variation in the data set. For example, if the heights are 150 cm to 170 cm, then the range is equal to 170 minus 150, that is equal to 20. This means the data spans 20 cm. Variance. Variance measures how much the data point differs from the mean. It does this by taking each value's distance from the mean, squaring it, and then averaging those squared differences. Use a different formula for population and sample data. A large variance means the values are more spread out from the mean. It's like checking how far each number is from the average in a squared way. The difference between population variance and sample variance lies in how much data we have. The population variance is used when you have data from the entire group, that is, the whole population. In this case, you divide by the total number of data points, that is n, capital N, because you are calculating the exact spread. On the other hand, sample variance is used when you have the data from just a part of the group or a sample. Since a sample might not perfectly represent the whole population, we divide by n minus 1 instead of n to slightly increase the result. This adjustment, called Bessel's correction, helps give a more accurate estimate of the true variance in the population. To calculate the sample variance, we start by finding the mean, which is the average of all the data points. We add up the numbers 150, 160, 155, 165 and 170, getting a total of 800. Then we divide by 5 the number of points, so the mean is 160. Next, we find how far each number is from the mean by subtracting 160 from each value and then squaring the result to make sure they are positive. For example, 150 is 10 less than 160. So 150 minus 160 square is 100. We do this for all the numbers and then add these square differences together to get 250. Since this is a sample, not the whole population, we divide 250 by 1 less than the number of points, which is 4. This gives us a variance of 62.5. The variance shows us how spread out the numbers are from the average. Finally, to find the standard deviation, we take the square root of the variance, which gives us a measure of the spread in the same units as the original data. Thus, we get 7.91 as the standard deviation. The population is the entire group you want to study. For example, if you're studying university students, the population would be every student enrolled at that university. Since it's usually hard to study everyone, we use sampling, which means choosing a smaller group or sample from the population. For example, you might randomly select 100 students from a university with 10,000 students. Then, with this sample data, you use estimation to make guesses or conclusions about the whole population. So, if the average height of your sample of 100 students is 160 cm, you estimate that the average height of all the students at the university is probably close to 160 cm too. Probability distributions. A probability distribution shows how likely different outcomes are in a random experiment. There are two main types, discrete and continuous. A discrete probability distribution is used when the outcomes can be counted, like rolling a die. For example, when you roll a six-sided die, the possible outcomes are 1, 2, 3, 4, 5 or 6. Each of these outcomes has an equal chance of happening, which is 1 out of 6 or 1 by 6. On the other hand, a continuous probability distribution is used when the outcomes can take any value within a range, like measuring the height of students. So, probability distributions helps us to understand the chances of different results happening in various situations. Multivariate data. Multivariate data looks at the relationship between different types of variables. For example, when studying departments and annual bonuses, we compare the bonus amount across departments like sales, engineering, and HR. In this data set, sales bonuses are $3,000 and $3,200. Engineering bonuses are $4,500 and $4,700. HR has a bonus of $2,800. This helps us see how bonuses differ by department. To find the average bonus for each department, we add the bonuses and divide by the number of employees. Sales bonuses add up to 6,200, so the average is 3,100. Engineering bonuses total 9,200, giving an average of 4,600. HR has just one bonus of 2,800. Comparing these, engineering employees get the highest average bonus, followed by sales and then the HR. There is a bag with 5 red, 4 green and 6 blue balls, making 15 balls in total. 2 balls are drawn one after the other without putting the first back. To find the chance that both balls are red, we multiply the probability of picking a red ball first, that is 5 out of 15, by the chance of picking another red ball after that, that is 4 out of 14. This gives a probability of 21 by 21. For the chance that one ball is red and the other is green, there are two ways this can happen. Red first then green, or green first then red. Each way has a probability of 2 by 21, so adding them together gives 4 by 21. This shows how to calculate probabilities step by step when drawing without replacement. Next problem. We have the math test scores of 10 students: 45, 50, 50, 55, 60, 60, 60, 65, 70 and 75. To find the mean, we add all the scores, which gives 590, and then divide by the number of students, 10, so the mean score is 59. The median is the middle value when the scores are arranged in order. Since there are 10 scores, the median is the average of 5th and 6th score, both 60. So the median is 60. The mode is the score that appears most often, and here 60 shows up 3 times, so the mode is 60. These measures help us understand the typical score and how the scores are spread out. Problem to calculate spread. To find the variance and standard deviation of these heights 160, 165, 170, 175 and 180 cm, we first calculate the mean, which is the average height. Adding them up gives 850 and dividing by 5 people gives a mean of 170 cm. Next, we find how far each height is from the mean, square those differences and add them together. This sum is 250. Since this is a sample, we divide 250 by 1 less than the number of people, 4, giving a variance of 62.5. Finally, the standard deviation is the square root of the variance, which is about 7.91 centimeter. This tells us how spread out the heights are around the average. Multivariate data, categorical versus continuous variable. The given table shows the relationship between gender categorical and time spent studying continuous for 10 students. The task is to find the average study time for males and females and to compare the standard deviations of study time for male and female. The study times are separated by gender. Male studied 2, 4, 5, 3 and 4.5 hours, while female studied for 3, 3.5, 4.5, 4 and 3.8 hours. The average study time for male is 3.7 hours and for females it's slightly higher at 3.76 hours. When we look at how much the study times vary, males have a standard deviation of about 1.11, which means their study times are more spread out. Females have a smaller standard deviation of about 0.65, showing that their study times are more consistent. This tells us that while both the groups study similar amount on average, male study times more vary than the females. There are 5 more problems from the same topic. We shall solve them one by one. 1. Tossing coins. When tossing a coin 3 times, there are 8 possible outcomes. To find the probability of getting exactly 2 heads, we count the outcomes where there are 2 heads and 1 tail, which are 3 in total. So the probability is 3 out of 8. For the probability of getting at least 1 tail, we use the complement rule. It's 1 minus the chance of getting no tails at all, which is just all heads. Since the chance of all heads is 1 out of 4 out of 8, the probability of at least one tail is 7 out of 8. Problem 2. Rolling 2 dice. When 2 dice are rolled, there are 36 possible outcomes because each die has 6 faces. To find the probability of the dice adding up to 8, we look for all pairs that total 8, that is 2 6, 3 5, 4 4, 5 3 and 6 2. There are 5 such outcomes, so the probability is 5 out of 36. For the probability of rolling doubles, both dice showing the same number, there are 6 outcomes like 1 1, 2 2 and so on. Thus, the chance of getting doubles is 6 out of 36, which simplifies to 1 out of 6. Problem 3. Selecting cards. In a standard deck of 52 cards, there are 12 face cards, king, queens and jacks because each suit has 3 face cards and there are 4 suits. So the probability of drawing a face card is 12 out of 52, which simplifies to 3 upon 13. For drawing 2 red cards in a row without replacement, there are 26 red cards total. The chance the first card drawn is red is 26 out of 52 or 1 upon 2. After removing one red card, 25 red cards remain out of 51 cards total. So the probability the second card is red is 25 upon 51. Multiplying these gives the total probability of drawing 2 red cards consecutively as 56 upon 52 into 25 upon 51, that is equal to 25 upon 102. In a survey, 60% of people like tea, 50% like coffee and 30% like both. The probability that a person likes either tea or coffee is found by adding the probabilities of liking tea and coffee and subtracting the overlap, giving 0.6 plus 0.5 minus 0.3, that is equal to 0.8. This means 80% like at least one of the two. The conditional probability that a person who likes tea also likes coffee is the probability of liking both divided by the probability of liking tea, which is 0.3 by 0.6, that is equal to 0.5. So there is a 50% chance that someone who likes tea also likes coffee. Problem 5. Bayes theorem. A factory produces 60% of its products in plant A and 40% in plant B with defect rates of 3% and 5% respectively. Using Bayes' theorem, the probability that a randomly selected defective product came from plant B is found by first calculating the total probability of a defective product, which is 0.038. Then the conditional probability is computed as the defect rate in plant B multiplied by the production proportion of plant B divided by the total defect probability. This gives a probability of approximately 52.6%, meaning that there is a 52.6% chance that a defective product came from plant B.